Suppose you have a sample of fluid and you want to determine whether HIV is present in your sample. First, you need a sticky surface. Pour the sample so that all proteins in the mixture stick to the sticky surface. Now, it is known beforehand that you are looking for HIV. Therefore, you can obtain a commercially available antibody for HIV and add it to the surface as well. If HIV is present, the antibody will bind to it. If HIV is not present, the antibody remains floating. The extra fluid is washed off. If HIV is present, the antibody remains after washing. But if HIV is not present, the antibody no longer remains in the well. Oh, forgot to mention, the antibody that was added had an enzyme screwed to it. So, if you now add the colorless substrate, it's going to produce a product, which you can detect as a visible color change. But if HIV was not present, then neither was the antibody, so you won't see a color change. But wait, there is a problem here. When we added the antibody, it can not only bind to the HIV, but it can also stick to the sticky surface on its own, because anything can stick to a sticky surface. This may lead to a false positive, in which you detect color change even though there is no HIV. So how to solve this? Simple. Block the remaining sticky surface first, so that nothing else can stick to it. Only then add the antibody. The enzyme portion can be changed to any detection method you want. If you used a radioactive label, it is called Radioimmunoassay, but the rest of the procedure remains the same. You can even use a fluorophore. The simple procedure we discussed so far is known as direct ELISA. There is scope for improvement here. First, notice that when adding the sample to the sticky surface, there is nonspecific binding. HIV, hemoglobin, albumin, pretty much any protein in your sample is going to bind to the sticky surface. This is undesirable because it decreases the sensitivity of the test. If HIV is present, it will bind, but in small numbers. So, we can improve the specificity by first sprinkling the surface with an antibody. Note that the antibody binds to the surface simply because it is sticky. This has nothing to do with its antibody properties. Next, add the antigen mixture. Normally, it would have stuck directly to the surface. But here, the antibodies already cushion the surface and selectively capture HIV, not any other protein in your mix. Therefore, we have more effectively utilized the total surface area in this case, by binding only our antigen of interest. This increases the sensitivity, and makes this method preferable for samples where the antigen you are trying to detect is present in low concentrations. Note that although both breads of the antibody sandwich are specific to the same antigen, they must be target to different sites of the antigen, because one epitope will already be occupied for capture. This improved version of ELISA, known as Sandwich, is the most commonly used in labs, especially to detect secretory molecules like cytokine. Now, another way the assay can be improved is if the detected signal from the enzyme or fluorophore was more amplified. We can do this by using a secondary antibody. Multiple secondary antibodies can be bound to one primary antibody, and the signal is amplified manifold. In summary, ELISA is a technique to detect the presence of an antigen in a mixture of proteins. It works by immobilizing the antigen to the surface of polystyrene microplate wells, which nonspecifically adsorbs molecules. Then, an inert protein is added to cover all unsaturated surface binding sites of the microplate wells. Antigen is detected by antigen-specific antibodies binding to the antigen. Finally, a signal measurement is made based on the secondary tag on the specific antibody.